Tiago asked me to do what you're calling a masterclass or a class in something that I kind of, I don't know whether you've been exposed to before, but I chose this topic. I teach a 10-hour lecture course at Imperial on broadly the numerical methods we use, these high-order CFD methods. And part of it is this solver of the incompressible Navier-Stokes that I thought might be interested in the standalone item. So usually what I do, I have a 2-hour format. I have a 1 hour kind of going a bit of the theory, and then I have an hour. We have some Jupyter tutorials and labs to play with. So we'll see. We're going to just do this for an hour. If there's some of you want to stay on afterwards, we can look a bit at the tutorials and see where that takes us. So this was the name of the course, but as some of you already know pretty well, because when I give the talks, we do these high-order finite element methods called spectral HP element methods. And broadly, the idea here is we try to discretize our problem here, the UK, into classical ideas of triangles, like we split in finite volumes or finite element methods, but we use these high-order polynomials. This spectral HP is adding P-type expansions into our basis. So I just need that for a little bit that follows on. I'm not going to talk too much about these sort of methods. We've got a couple of terminologies: spectral elements, HP finite elements. If you go to any of these conferences, you'll hear people talk about continuous and discontinuous and flux reconstruction. That's just part of our overall community. All I want you to remember now for one of my slides is we have H-type discretization in our domain, and then we have these polynomial expansions we apply with each subdomain. So what are the tools or the cases we'd like to be applying it to? Now, Bruno Carmo told me some of the people here today might be doing his stability course, so I thought this was useful to highlight. The flow solves I want to show you is what's the numerical method we apply for these sort of flow solves to the top here. Here we've got flow path similar. This is a stability analysis, which is hopefully relevant to that course. We've also got more complex geometries and flow cases. How do we get an algorithm from the Navier-Stokes solver to run on these type of applications? Well, if we end up doing another one next year, we can always do the bottom line. That's the compressible flow analogy to it. So mainly we're looking at incompressible flow today. So what is the structure of what I want to go through? I have to make sure I got my notes. We're going to, remind us of the Navier-Stokes equation and some of the choices we're going to make in this scheme of what we can get away with in terms of explicit and implicit time discretization for those cases. Now, we heavily use this scheme called the velocity correction scheme I want to introduce, which goes back to the early 90s. I'm sufficiently old to be there. I'm worried most of the people in the room will wonder why we take an algorithm from the early 90s, but we're still applying it. One of the things that was intriguing to me, so when I was a PhD student, as some of you know that sort of area now, we just applied the scheme and we weren't quite sure why it worked. It took 12 years later, so a couple of mathematicians I'll show you came up with this velocity correction scheme analysis, and that's what I want to lead you through, because it gave me a sense of the building blocks behind these algorithms, and therefore why it might be useful if you go to change it, if you try to apply it for different sort of applications, how do you get those key ingredients. And one of the unusual factors of this scheme is that you have a pressure, so-called pressure Poisson solve, which needs boundary conditions. But for those of you that have studied Navier-Stokes equations, strictly speaking, you don't need boundary conditions on pressure. You only need boundary conditions on the velocity components. It's strange to think of a scheme having boundary conditions for pressure, but this analysis kind of highlights where those come from and whether we have to think of them as boundary conditions or actually just solving the main scheme. And then at the very end, we'll see if we don't run over, because I thought some of you are doing the Navier-Stokes equations. I can show you how we've been applying it to the linearized Navier-Stokes equations, not just the nonlinear equations. Okay, here's the description, of course, of the Navier-Stokes equations. I think in this group, hopefully you'll be comfortable enough with me writing it in, we're mainly going to see it in vector form when I'm teaching this to our final year undergrads and the MSc students. They prefer to see it written out component by component, but it gets too much to write down if we do that. We've got two key ingredients here. We've got our convection type terms, and I hope we're all comfortable with the idea that this just represents information that propagates forward in time. So if I have a scalar quantity and I have a 1D problem, let's say I've got x and time, there's a direction, a velocity direction, that some information will propagate and of course will remain the same in magnitude. So that's our effective terms. And then of course the complement to that, we've got these red terms, the diffusion operators. So hopefully, again, all comfortable with the idea that the action of that is going to be that we have information that will, in theory, be propagating forward at our velocity u. But this time we're expecting stuff to be smoothing and diffusing in time. So if this was x time and our solution vector, this is what we'd expect to see. Now, I printed some notes so you can write things. Mainly the reason when I lecture, I write things is because I speak even quickly, but if I don't write anything, then we're going to get through this in 15 minutes. So interrupt me otherwise as we go through as to what the relevance or not of what you understand from these bits. I think this bit's okay. We'll see how we get to the next few steps. So we deal with these higher order methods. Why might we want a scheme that can deal with some stuff implicitly in time and some stuff explicitly in time? It's kind of useful to go back to a scalar problem, just sort of an advection diffusion problem, just taking those two components I was just drawing, and ask what kind of time step restrictions do we get from each of those schemes. So in a purely classic finite difference sense, if I was solving just an advection problem and I had an Euler forward scheme, we get this classic Courant-Fredericks-Levy condition, which says my time step restrictions to propagate this advection term ahead of time is dependent on the mesh spacing and the speed of the velocity. Essentially, information's got to propagate on the discrete mesh no faster than the physical information can propagate. That's what that quantity tells us. There's an analogy to this with the diffusion operator. Here, though, we see that the time step restriction comes as a bit more severe. It has this delta x squared type component for the classic finite difference type scheme. So this is the scheme, this is the term, which is going to be linear in our original equations, but we want to bring implicitly because it has a tighter time step restriction. Now, if you're interested in other numerical schemes, it doesn't really matter that it's a spectral HP element scheme, but the schemes I just introduced, you can think of the mesh spacing as being this delta x, but divided by that polynomial. We have this polynomial expansion, it's the polynomial squared. So in this case, it says my advection, okay, it's restricted by the size of the mesh. Our meshes are quite big, so delta x is big over p squared. That sounds bad, but there's very little we can typically do about the restricting the advective speed of these spectral element schemes. But this is the one I wanted to highlight why we do it implicitly. We have a time step restriction goes with the size of the mesh divided by the polynomial order to the fourth. If we get up to polynomials order 10, this is going to get ridiculously small when all I can do is time march. I've got to have some scheme that brings something implicit in time. Okay, so here is the top level of the scheme. Here's my Navier-Stokes equations written in vector form. What does this velocity correction scheme all around? So here was my original statement. Originally, Orzag, Israeli, and DeVille, and then Carnier-Dakis, Israeli, and DeVille introduced this in 1991. So whatever, 33 years ago. I don't know. Even Tiago, I don't want to ask your ages. I'm wondering if anyone was around. I can remember the day, but you can't. And here, so look, it's 2003. Maybe we're getting into the realm of possibility of your birth ages now. Some 12 years later, these guys came along. So originally they called this a stiffly stable scheme, and I've adopted this velocity correction scheme, which was named by Gourmand and Shem. So what do? We take our advection terms and we time march them explicitly as we're describing. Then you have two other steps in this scheme. You have a splitting scheme. We solve independently for pressure, and we've got to, we take essentially the advection of the Navier-Stokes equation, and we get this U plus scheme here. And we feed it into a Poisson equation of pressure, so-called pressure Poisson equation. And then this last step is an implicit discretization of the diffusion terms. I think we'll see in a moment the steps where they tend to come from, but here was our diffusion viscosity. We've taken it, I like to think of it, taking it to the left-hand side, and we've got all this term here at n+1, this term essentially discretized at n+1, with the nonlinear terms, the convective terms are all being dealt with at the previous time levels. So what is the heart of this scheme? So here's the cartoon of it, which helps us range. So every time step we're going to make, we explicitly calculate our advection terms, and then we solve this so-called Stokes problem, but we solve it component by component, which makes it more efficient. So the pressure Poisson equation is a scalar equation. The Helmholtz problems are also then, we can solve it, the U component and the V component. So it meets my demands. I've got something that's implicit. So where does it actually come from when I write it out in a more complicated form? So here's again my Navier-Stokes equations. We're going to use two techniques here. We're going to use backwards differentiation in times in our standard Taylor expansion and extrapolation. So what have we got? If I go and slow us down a bit, and we think of it in terms of our finite difference scheme. If I've got time level n plus 1, time level n and n minus 1, what I'm essentially doing is approximating this du dt term by one value at n plus 1, that's what's making this bit implicit, plus I've got minus a u hat term here. If it was a first order scheme, I would just use these two time levels. So that's just for these two bits. And if it was a second order scheme, I'm going to use these and these to get a slightly higher approximation. You see in this scheme, if I'm using my u hat term here, is dependent on time level u and that time level u of n minus 1. Now, I'm presuming in my ordinary courses we've done Taylor expansions. Whenever we normally teach numerics, we teach finite difference methods, and we get Taylor expansions, and we just repeatedly hammer students with that. I'm hoping that's been your previous education at this point. So that's get a subtle nod for someone, or we're not sure. I don't know. Okay. All right, so then the other technique we've got now, the nonlinear terms. The reason we can put a term in at n plus 1 is this is a linear term that only involves the velocity on its own. Of course, the nonlinear terms, this n of u involves u times u, and so if you're going to bring anything implicitly, you have to think of solving stuff in Newton-type schemes. So we don't want to do that. So mainly we only know information at the previous time level, right? So what can we do in that case? We can think of our three time levels, and we've got an n plus 1 and then minus 1. And we only know the values at n and n minus 1. That's what we see in this extrapolation. If I'm going to do a first order extrapolation, all I can do is take the information of the previous time level and say, well, that's going to be my next best guess for what happens at time level n plus 1. So I can just take that to this point. If I want to maintain a slightly high order accuracy, a second order accuracy, I can take one larger step and I can say, okay, I can use time level n minus 1, and extrapolate using my Taylor expansions to get some approximation at n plus 1. Okay, so these are the two main building blocks that get me to the scheme I've just shown you if I'm happy that I can backwards time integrate and do that extrapolation using finite difference method. So if I skip forward, what's it going to do? I'm going to take essentially my my backwards difference formula, put it in that, and that's going to give me this term here. So that's, you can see how they analogously look. I've got the alpha u at n plus 1 minus this u hat. U hat is just hiding which order scheme I'm using. And then the other sneaky bit I'm going to do here is we're going to take extrapolation term. So we've got our u star term. Instead of, I haven't got u of n, so I'm taking my u star term, put it in there, and that's what's appeared with this u star here. Okay. I can deal with the stuff on the right-hand side because this is already at n plus 1, so that's the diffusion terms are linear, so I can bring them implicitly. And almost with the scheme now, I've got everything I wrote in that first discretization of my splitting scheme. Okay. What happens next then? So I got this pressure Poisson system I mentioned. I just want to see where that's come from. So here's my discretization using Euler backwards differentiation for the time discretization. And when these sneaky stars in, we can just assume there's been an extrapolation, extrapolate the nonlinear terms. The next part of the construction of this scheme is to use splitting, or a Strang splitting that comes from. So what happens now? I can think, I'm going to write this down in 3 steps. I can take my du dt term and think of it as three separate steps. So in this first step, I've got a u hat here, but I've introduced this u plus. So I've got something that looks like a time derivative, which just involves the affection of the nonlinear terms. This takes my previous information at time level n or n minus 1 up to this u hat type term. Then I can think, you can see I've then got if I've taken this pressure term and done a splitting, I've got a u plus with a hat on term. These are sort of pseudo velocities, if we like, at the intermediate steps of our time stepping scheme, minus the u hat. And at the very end step, so that second step's involved the pressure. At the very end step, I've got the viscous two terms carried in here. and I've got this u hat term in here. So if I was to look at the cancellation, if I think of this backwards, if I substitute this back in for this term, I substitute this back in for this term, then I recover the equation I've written there. Okay, it's just a sort of purely, I introduced two auxiliary variables, u plus and u hat plus, and I can then write three different things separately on the right-hand side. And this more or less gives us our scheme that I introduced at the beginning, this velocity correction scheme, in terms of its building blocks. We've got our first step, which was this blue stuff before. Now, recall this terms here were my backwards differentiation. And the second nonlinear terms, this was my extrapolation. So that was hidden. This n plus term is this extrapolation. That's where I got those ones from. And these plus, and these are the previous time level parts of the backwards differentiation. So that's fine from those two elements that I introduced from the first two steps. This is the one that causes a bit of a headache, and I'm going to have to come through. So what really the next few slides or the next 10, 15 minutes are about is, why on earth do I get away with just solving this thing on its own? So this red bit I'm going to save for itself. Essentially, half looks like the stuff on the right-hand side. If I take the divergence of that, I get something like this. But then I've got all these headaches of strange boundary conditions come in. So let's leave that one for a moment and come back to it. And the last part of the splitting scheme, well, I can just rearrange the equation. If you accept I can time march the blue stuff to get the nonlinear terms, if I could solve for the pressure in the second term, then finally I know my u plus hat term, and this is just a Helmholtz problem. That's linear discrimination, the Helmholtz problem. So if I rearrange this, here's my u at n plus 1 times the Laplacian. I've got my time discretization term, or the implicit part of that time discretization term. So this is the matrix problem that I would have set up and solved, but it's linear. So in any of our numerical methods, if we're doing finite difference or finite volumes, we'd expect to be able to solve this sort of problems reasonably on a computer, and all the stuff on the right-hand side is explicit. Right. So I take a little breath. Any questions for the moment? I warned you if I didn't write anything, we'd go even quicker, but okay, so, okay. Oh no, I'm good for that, I think. Right, what about this funny pressure term? Why have I got this bit in the middle, and why do I worry about this so much? Well, when we implement this stuff, this is where it all tends to go wrong, and when we spend our lives debugging is explaining this term in here. So, what are my key steps here? I've got this right-hand side. I want to take the divergence of that. So let me go. My slide's gone. Here we go. Yep. Let me take. So if I take my second step for the splitting scheme, and if I simply take the divergence of this term, so essentially I'd be taking the dot product of this, and if I take the dot product of that, I'm going to get this Laplacian operator. But what happens on the right-hand side? I've got divergence on this u hat, so that's what I wanted in this previous scheme we wrote. So that looks like this term, but I can't do anything with this u hat term. It's u plus hat term. So the only thing left to me in my scheme, which I just sort of willy-nilly wrote down quite quickly, what I now realize I'm doing is I'm implying that I got the divergence of this flow quantity of u plus of hat. I'm setting explicitly to 0. Now that's not really the velocity at n plus 1. That's not the divergence condition in the Navier-Stokes equation. This is a pseudo velocity that I'm forcing to be 0. So that's what's happening in this splitting scheme, is I must set this quantity to 0, not the u of n plus 1. So in all these schemes, I refer to these splitting errors, and this is where our splitting error comes in, that instead of satisfying the velocity at n plus 1 with this condition is the divergence of it is equal to 0, we satisfy this pseudo velocity that looks like, or it's half extrapolated the velocity you want at n plus 1. And that means we have an error in our solution, and the splitting error, which scales of order the time step squared. So if we recall back, I deliberately only introduced at the time my backwards difference formula and my extrapolation formula to give me delta t squared accuracy. So that's no worse than the type of accuracy I get from those sort of finer difference approximations. So that's why I get away with this when I'm time marching the Navier-Stokes equations. If you wanted to solve something to steady state, and if you wanted to make really big time steps, you'd be worried about this sort of error creeping in. But we accept that because it's not inconsistent with how we've time discretized our work. Okay, so that takes us to our pressure Poisson equation. But I supposedly need some boundary conditions for this thing. Okay, I can't solve an elliptic problem that have no boundary conditions. That's a very ill pose. But when I started my discretization for the Navier-Stokes equations, I only really needed usually to come up with conditions on the velocity. I know there's a no slip condition, say on the surface of something that's solid, or I might know some information about the free stream, and I'd know that that was velocity conditions. I wouldn't usually be told anything about the pressure. So this is where the scheme seems a bit convoluted. I have to come up with some sort of pressure boundary conditions. And this is where in the original work I said from the early 90s, 91s, this is what they did is said, well, I know I've got the Navier-Stokes equation, so I've got du dt plus the nonlinear terms n on v is equal to minus gradient of pressure plus the viscous terms of velocity. What I could do is I could take that equation, and if I dot it with n, I've got something, so the gradient of p dot n looks like a Neumann boundary condition dp dm. Okay, so if I take this equation, I say I want to know the solution at n plus 1, so I have to evaluate everything again at n plus 1. So I put this all at n plus 1 in principles, but I can use the tricks and I showed you a moment ago for my extrapolation. And I can extract out a Neumann boundary condition for my pressure Poisson system. So at n plus 1. So that might have worked, but there are two subtleties of this problem that we want to go through. One, okay, I've got this nonlinear term in here, which I can't possibly evaluate at n plus 1. But we use this extrapolation type idea in a moment, so I can do the same trick. I'm going to say, I don't know it at n plus 1. Let's take the values n and n minus 1 and push it forward in time. So that's my first step here to replace n plus 1 with n. But the other question and the challenge of this scheme is, I've already admitted when we set the pressure Poisson equation, we didn't set the real velocity at n plus 1 to 0. We set this u hat, a u star quantity to be equal to 0. So what they did is they replaced this Laplacian and used a very neat vector identity. It's kind of hidden in here, which it's written down here. It says that the Laplacian of the velocity can be written as the gradient of the divergence of u, that's the thing that we'd like to get set to 0, minus the curl of the u. Now, I don't even know where this comes from. If you want to look it up, you should go on Wikipedia. That's the one that's there. It's just stated as all the many vector calculus. This has nothing to do with fluid mechanics. This is purely vector calculus. But why it's attractive to us is because what we can do is try and set this term identically to 0. We know the divergence of u in our case is equal to 0. So I try to enforce as the quantity idea the divergence is going to be 0 at my next level by using this curl form of the diffusion operator rather than this Nabla squared Laplacian type operator. Okay. So I do that, and now I've got a pressure boundary condition for my problem that dp dn n plus 1 is equal to, here I put an extrapolated quantity of this curl operator, so that's enforcing divergence freeness, and then the stuff I don't know I extrapolate from the previous time level. In principle, I know du dt, if it was time dependent, it's only at the boundaries. We don't enforce this everywhere, so I should be told that condition, so that one's fine. I can leave that out. And the nonlinear terms are then being extrapolated. So that's the last step here. I mean, so let's mark that down. We've got this is enforcing divergence free. And these are, of course, just my extrapolations. So that's what I've done to get to time level n+1. Okay. Now, my theme, though, is what confused me for ages, what confused a lot of people in that missing 12 years is why have we got boundary conditions for something we never needed boundary conditions from? I've kind of taken the Navier-Stokes equation, discretized it, taken the same Navier-Stokes equation and derived the pressure boundary conditions from it, and somehow that's okay. It turns out to be okay, but it seems a bit of a strange thing to do to repeatedly use it in this manner. So what else could we do? Where do the pressure boundary conditions come from? This is the work from Gaumond and Shen that I mentioned. They had a different way of viewing this problem, and I kind of just want to highlight that to you because it reassures me that the pressure boundary conditions in a certain setting aren't necessary, but another setting we can justify why it's a valid assumption. Now, what I want to do in this step is apply something that's like the derivation of the finite volume method. Now, one of the disadvantages of doing this as a one-off, usually when I've taught the previous 3 courses, I've introduced the finite element method, and I don't know if that comes up in your courses at this point, whether you've seen that. I'm not looking at any gracious nods. Doesn't normally come out. Okay. What normally in the construction of a finite element and even a finite volume method, if we had something we were solving like the Laplacian is equal to a force, the steps to solve it, what you do is you multiply it by a weight function. I might multiply it by a v, and then you integrate that. The curly brackets I'm going to introduce in a moment are the integration over the domain. So I do a v over this domain. I get a so-called integral form of the differential equation. And then I'll apply the divergence theorem or integration by parts, and we'd normally end up with my Laplacian operator looking something like the gradient of v in a product with the gradient of phi is equal to, plus a boundary term. So I'm going to introduce some angle brackets, v theta phi dot n is equal to v comma f. I'm going to go through that step in a bit more detail in a moment. We've not seen it before, but that's just kind of a reminder. If you have a finite volume method, that's the steps that would take in place. So why is this helpful in this construction? Gaumond and Shen said, well, I'm going to take the Navier-Stokes equations, and I'm not going to think of them in a strong form or get the Laplaces. I'm going to simply multiply them by a weight function. And their choice of the weight function was this gradient of q. There's a reason they want to write it. This term here comes from the Poisson equation, from the pressure term, and it looks like the weak form of the Laplacian that normally comes out of the finite volume method. So they wanted to jump immediately to that weak form and say, I think I should be solving, when I'm solving this weak pressure Poisson equation, this equation directly. So why does that get me to these boundary conditions? So I'm going to show you, let's put these ones out, and I'm going to jump out and come back to this. So using divergence theorem, I can take any term in this weak form of the equation I've shown here, apply the divergence theorem to get stuff that's in the volumetric time plus stuff that's on the boundary. And this stuff on the boundary is going to justify my choice of these pressure boundary conditions. So I'm going to take a little aside because I think it'll help us slow down fractionally and just remind us of those steps of the divergence theorem. So if we remember our, I don't know, when it's in your course, at various courses, we teach at some stage in our first or second year that I don't know if they get it, and then we repeat it a million times and they eventually get the idea of the divergence theorem. But integration by parts for a vector quantity. So if I have a quantity u, which is a vector, I take the divergence of it, I integrate it over any volume. That is equivalent to that same vector dotted with a normal integrated over the surface of this volume. So here's my ds, d omega, sorry. Okay, so how do I want to apply it in that slide I had it in rather condensed form. So I've got terms that look like the q times, say, a velocity, a vector, a scalar times a vector. I know that that scalar quantity times a vector, if I multiply it out using the product rule, Q is a scalar, so that's the gradient of Q gives me a vector. I dot it with the vector that is U. And I've got the other part of the product rule, the scalar dotted with the divergence of U, just one, 2 steps. So why does that help me? These are the 2 separate terms. The gradient of Q we saw I introduced on that previous slide I want to use, multiplied by some sort of vector quantity. On the left-hand side here, I've got a divergence term. Now, we said in the construction in the finite element method, we integrate over a domain. So I can integrate all of these quantities over my solution domain. So this gets over omega d omega, and here over my domain d omega. And if I apply my divergence theorem on this left-hand side term, what happens? I've got that this term here is equal to the integral over the surface now of Q u hat dot n bar ds, and then I've got these other 2 terms, gradient of Q dot u bar d omega, plus my Q divergence of u hat d omega. So the term that I'm starting with on the previous slide was this term. I want to transfer this gradient operator onto the right-hand side, and I'm going to get a term that looks like this. So by applying the divergence theorem, I want to rewrite this in the form that any of my terms, that's the gradient of Q dot by the vector integrated over the solution domain, is equal to minus this term, if I've taken it to the other side of the equation, Q divergence of u hat dx, plus I've applied the divergence theorem. This is now something this is integrated over the boundary of that control volume. So that's Q u hat dot n ds. So the notation I've got that we're going to go back and follow is when I use the rounded brackets, that's relevant to an integration over the whole control volume. That's going to give me a minus sign times the transfer of the derivative now onto the u term, the vector term, over the whole volume. Plus, when I use the angle brackets, what I'm going to mean is an integration over the boundary of the problem. Now, I suspect some of you have seen that before, that's fine, but at least it's a reminder those are the steps. Now, if I go back to those slides, this is I want us to really just to be convinced that this equation exists, this last layer. What did I do when I had my terms? Here, so I have my Navier-Stokes equations. I multiplied them by this gradient of Q term. We'll see why that helps us in a moment. And then I've got these rounded brackets, which just meant I integrated over everywhere I want to solve my problem in. And then now I'm applying the divergence theorem. I can take this first term here, which is the gradient of Q times the du dt term. That's a vector quantity. That's mathematically equivalent to minus the Q, so there's no gradient to that, times the divergence of d hat du dt term, plus something on the boundary, Q times du dt dot n. Remember, these angle brackets just means the integration on the boundary surface. So that's this first term. This is what I'm doing all the way down. We've got our nonlinear terms. It's going to give me something that's on the boundary. Remember, we're trying to get pressure boundary conditions. They had these nonlinear terms evaluated in our boundary conditions on the boundary. We've got a term here for this third term, when we construct it, which gets us back to something that looks like the Laplace equation now. Here's my pressure Poisson system reappearing through the divergence term, and then I've got a condition that looks like the dPdn term. And in the last step, I've done exactly the same. I've taken the Laplacian type operator, applied divergence theorem, but sneakily, what have I done? I've imposed that I've used that vector identity. First, I've changed it to a curl. So the Laplacian of u was equal to the gradient of the divergence of u. Divergence of u we take out as being 0, and I get a curl. When I apply next my integration by parts, I get a Q, and this Laplace gradient operator is now on this curl operator. Here's a quiz for my students normally. What is the divergence of the curl? By definition. Exactly. Mathematically, it's 0. So we get a little bit of a win here because this stuff is identically equal to 0. So this term through this integration goes away, and on the Laplacian, I only seem to have stuff that acts on the boundary of the curl. I got a volumetric term here, but I only have to, under all this manipulation, worry about something that appears on the boundary. Okay, nearly there. So this gives us our last step. So this was the building block of Gaumond and Chen. Through realizing that kind of bit of analysis, they said, well, doing all that integration by parts, it says that it's pretty almost equivalent to something that looks like my Navier-Stokes equations. Here is how we'd normally have written this is the divergence of the Navier-Stokes equations. So this looks like the pressure Poisson system, but plus a lot of terms that actually need to exist on the boundary for it to be equivalent. And this is my pressure boundary condition that's come out of this. So if I want to think of the pressure Poisson system in a strong form, which I generally like to think of mathematically, here's my pressure Poisson problem. I need an equivalent set of conditions, these angled bracket bits, that give me this pressure boundary condition that I'm imposing to get back to this weak form. So here's the Navier-Stokes equation, just multiply by a gradient of a scalar. Done nothing mathematically too unusual. I don't know why I multiply. You think, why am I multiplying? But it's still the same equations. If I take an equation, I multiply it, and I think it's the same set of equations, it's got the same solution. If I do that and I integrate it over the solution domain, it's still got to have the same solution as the strong form of the equations. But I can recast it as this alternative form, which is exactly what we ended up solving, but we didn't know why we solved it in our previous type formulation. And so you may never need to recall that again, but it's kind of reassuring if you want to use these schemes. This is the kind of manipulation, or this is the analysis that they came up with to explain its construction. So if you were trying to introduce, and we have been looking now, trying to make the scheme more implicit, what does it do to the boundary conditions of this problem? Or if you wanted to add a source term that was to do with, well, in this case, like a porous medium flow or a Brinkman equation, how would it affect the boundary conditions of setting up these type of problems? That's why I generally find it kind of useful. Okay, so I think at the end, I had some more examples. These are the schemes, the type of problems that we can solve using that scheme. This is what we're applying time and time again. I think there are a couple of observations I would give you as one that's beneficial and one's a word of warning. So the beneficial one is we can play other tricks in how we discretize our problems. If we have something that's very regular in one dimension, in this case, it's flow past the cylinder, so the geometry doesn't change in the Z direction here. These IMEX type schemes can be quite powerful because the Laplacian, this diffusion term, the stuff we bring implicitly is linear. If I have something I could expand, in my case, like a finite element or finite volume discretization in the 2D domain, if it's not changing in the third direction, I could do something like a Fourier expansion in that third case. And what that does when I apply a Fourier expansion to this Laplacian is it just makes a series of 2D Laplacian type operators. Now, why is that helpful? It means I can solve something that's really fully three-dimensional, but as a series of 2D problems, and I can afford to solve that directly. The implicit terms, right? I've got to make a matrix, I've got to invert it, and then hit it with that problem time and time again. I can afford to store that on the computer and solve that. And that's in terms of high-quality papers, say in the Journal of Fluid Mechanics, the Fluid Mechanics archiving, I'd say 70% of the papers in this topic are using this discretization. That's because we got away with that.
But then you get oscillations in the Z direction for the velocities if you have vortexes?
Not for vortices, you won't get oscillations. I mean, if you have discontinuities, if you have jumps, you can do. And the only other subtlety is that if you have very high frequencies and you don't have enough Fourier modes, then you can get aliasing type problems. So you can get build-up of energy in high frequencies. They tend to have a drain, but not. So there's an assumption that it's periodic in that direction. As long as you keep that periodicity, that should work fine. But if we're trying to solve the same problem in 3D, and for the car type problem, we have solved it in 3D. Yeah.
Just to compare with the solution, you might have higher stations in that direction. I don't know if they're also symmetrics.
Yes, so they can edit. So at one frequency, you can multiply by a Fourier thing, it will put energy into a higher frequency. And so it depends on how many Fourier modes you have. But let's say you have a lot of turbulence and you only resolve the first 50% of the spectrum, then you have to worry about aliasing errors coupling back in. But I should point out in the spectral element method that happens in the 2D plane as well. We have a mini polynomial expansion, and that same coupling happens. And then that's a completely different discussion on how we stabilize these schemes. We tend to use de-aliasing and something called spectral vanishing viscosity. So kill off the high energy when you're under resolved. But if you fully resolve it, if you increase the number of Fourier modes, it will then run without any stabilization. Yeah. I mean, so now the problem is how big is your Reynolds number, and therefore how small are the scales, and then how many Fourier modes you need to capture. That's the kind of the machinery if we want to get to. But if you want to go to the Formula One type cars or the kind of, then everything's 3D, and then you have to go to iterative solvers for this implicit part of the scheme that we've done. We raise the stability, so I put this slide in to remind me. When you do really high Reynolds number, and often when you solve the incremental Navier-Stokes equation, there's something called an IMSU condition. You have to be careful of when you discretize the pressure equation, you can't have too many degrees of freedom. You over-constrain the problem, and you get to a so-called locking or IMSU type problems when it's the Navier-Stokes equations. So this scheme, for ages we run it with ignoring that. It doesn't sit for moderate Reynolds numbers, that wasn't a problem. As we pushed it to higher and higher Reynolds number, then we have seen this IMSU or the locking type problem. And what we tend to do is run the Poisson system at a slightly lower polynomial order in our case. In finite difference, they use things like they use the center of the stencil, and the corners are for the velocity. So just be aware for the incompressible solvers, you have to deal with that behind the scenes. Okay, and the last bit I was going to introduce, I thought I'd bring up was you've been looking at some of you have been looking at the linear Navier-Stokes or stability equation with Professor Calmo. He told me, I think you get on the code now, examples to look at stability analysis. So how does that relate to this velocity correction scheme we've been doing? Well, okay, so if we take the linearized Navier-Stokes equations, the idea here is you take the base flow and you want to solve for perturbations that might grow or decay on top of that base flow. So we take our solution. If you take this linearized term and shove it into the Navier-Stokes equations, the nonlinear terms become the two non-symmetric advection type terms that we were just looking at. The linear term, of course, remains exactly the same. So in the example here of a cylinder, you might have the base flow vortex shedding past the cylinder. And then there's some Floquet modes analysis where you can do the linear instabilities on top of that. So how can we relate that to solving these velocity correction schemes or the advancing in time? Mathematically, you look at the linearized Navier-Stokes equation as an ODE problem, and you'd like to find the eigenvalues of this L operator. So I can write the linearized Navier-Stokes equations as this big L operator. It's dependent on the base flow, the thing times the time step. But there's an equivalence way of looking at it. You see, I don't have to solve my ODE problem. I could think of something being integrated in time, and I get this so-called Mondronomy operator. I take an initial condition, and I time march it some time tau to a future time, and I get a u prime at time tau. This is where we apply our splitting scheme that we've just been talking about. We take any initial condition. Instead of the nonlinear terms that I was referring to before, I replace them with the linearized Navier-Stokes equations. Remember, the big U's here are known, and the little U's are just perturbations on that solution. And then I still have to solve the Stokes problems that we talked about before with the pressure Poisson on the implicit scheme. That was all identical to the scheme I was just showing you. And so I time loop that up to some time tau, and that gives me this operator. Essentially, I look to find this A operator, which is the time integration, and literally the exponentiator from 0 to tau of the linearized operator I'd like to find the eigenvalues from. So in this case, why are they linked? Well, the instabilities, the things we'd like to know most about the instability of the linear right associative equations, we'd like to find the eigenvalue with the largest real part of this L operator. So that tells me that why do I want the real part? Because the eigenvalues, it's only the real part that grows in time. The imaginary part is just stuff that's oscillating back in the frequency space. But that's equivalent for this, taking this A operator, this Montgomery, the time step from going time 0 up to time tau, of does a perturbation from initial condition grow sufficiently well at some later time? If I find the eigenvalues of that A operator, the largest one will be the most unstable mode. The largest one corresponds to the value that has the biggest real part. So what do? We take this time marching scheme, we fit it into a QR type algorithm. So you create something called a Krylov space. Each one of these operators, I get a random initial condition, I time march it, that's what this A operator means to some time tau. I then take that again and I time march it again, and I get an A squared, and that builds this Krylov domain. And then we use this QR factorization, or it's all built into this Arnoldi pack. You essentially approximate a very high dimensional problem by this lower dimensional subspace, and you can find the eigenvalues of that lower dimensional subspace, and those lock onto each other. And that's how we find these instability modes in our fluid mechanics type setting. Okay. That's pretty much it for me. That's all I was going to say. The last stuff is a bit extra because I think that's more related to some of the coursework you've done. Now, what I would normally be doing with my class is going onto these Jupyter labs, and I'm happy to spend. I don't think you necessarily need the online part, but for you to have a play if you want with using these tools yourself and seeing the sort of flow characteristics back out of this. Okay, so I'll finish that there and see if there's any questions. Then we'll see who's left over for the next hour. Questions?
I have a question, but maybe it's a too mathematical question.
I don't know. After this one,
but it's about this technique to find the most unstable eigenvalues.
Yep.
Because your objective is to find the ones that have the biggest number, the biggest values, because they will reach the highest instability. It's less, and you use this technique to the field of subspace to find these eigenvalues. But I would like to know why this technique, using this Arnoldi techniques with those eigenvalues, why does it lead to the biggest eigenvalues for the stability of the operator?
So it's Arnoldi is so there's a technique finding eigenvalues just called the power method. I don't know if you come across this. So if I take a matrix, I get a perturbation, I hit it with a matrix, and then I get an outcome, and I keep repeatedly doing that. You can show that the largest eigenvalue is the one that's going to grow the most because it's got the biggest multiplier, and it'll go if you hit it again and again and again with this, eventually the largest one will become so big compared to the other ones, that's all you're left with. You get the idea? So if you think of, if you had a 2x2 system and you had an eigenvalue of 10, an eigenvalue of 1, and multiply it, that 10 times a thing, it's going to come. The 1 component is there in the first iteration, but now let's do 1,000 iterations. That 10 has got enormous. That's the only thing you get left of the pattern that comes back out of the problem. Now, the power method is good when the matrix is symmetric. You can think of the Arnoldi method as a way of when it's not symmetric and it's got complex eigenvalues. And it's just having to do a bit more playing with dealing with the imaginary component. But in this scheme, we hit it time and time again. So I said we build this Arnoldi space. We only do that once, and then we have to keep rebuilding it and keep rebuilding it until the largest eigenvalue dominates, and then we extract that back out. So in some sense, it's easier to think of, it's easy to get the largest eigenvalue. What I can't do is get all the others. The others are hidden from me because they're too small and I can't get the whole matrix out. I mean, in this method, it's a block method, so you can get n eigenvalues possibly, but the downside of this is the largest eigenvalue pollutes or masks anything else. If you want many eigenvalues, then you have to go and look at other schemes to do that.
I understand.
Okay.
Any questions?
So how do you do the initial calculation? You put
The stability stuff.
just random?
Just random, typically. Random and normal. Usually because the random condition is usually divergence 3, we might do that and then discard that first one and then start from whatever that second step. But yeah.
I have a question, really quick one. As I mentioned, I'm more interested in design optimization. Are you able to compute sensitivities, or are you planning to?
Yeah, well, so there's a technique related to the stability analysis which looks to find the adjoint modes of the system. So
then you can do it.
Yeah, but it's quite complicated. So we forward march the linearized system, and then we backwards march the adjoint system.
Yeah,
and that gives me A times A conjugate operator, and then I can find the eigenvalues of that, which is then the singular values.
and so you have a transient.
And then we get the transient. Yeah, exactly.
Oh, that's really good.
Yeah, but a bit more expensive. so that's the one problem when you're doing the design optimization, to put that in the middle of an optimization.
Yeah.
It is pretty expensive, but yeah, that's definitely possible for this linearized stuff. Well, and we have some of the tools to do that.
That's okay.
Questions? No, that's thank you, sir. Thank you, everybody, for attending. For us to learn this, and it's quite of an honor to host Professor Kaiser. So great to see everybody here, and wish you guys now take this forward. Professor Kaiser will be here from time to time, so please feel free to also interact and let us know at RCGI that we can advise these interactions. Okay, thank you, guys.
Thank you.
Thank you.